Let's continue with our discussion of the finite difference time domain method in one dimension. And let's attack the problem of terminating the grid. So let's sketch out what we got going on here. Okay, here is the spatial dimension, and here's the time dimension. And we have uniformly sampled points in X, like so, and likewise in time. And so these are the EZ samples, so the Z component of the electric field at time step Q and space step M here, where this would be M equals, let's say this is 1, 2, 3, and 4, and then this would be Q equals, say, 0, 1, 2, and so on. Now, in the Yi grid, which we talked about last time, the magnetic field values are not at these same grid points, but they're offset by 1/2 step in both dimensions. And so we end up with something that would look like this. Here would be the magnetic field sample points. We shift them to the right 1/2 step and up in time 1/2 step. So it would look something like this. And let's even go one more here. So these are the HY at Q plus 1/2, M plus 1/2. And even though we suppress that plus 1/2 when we actually program it, just to follow the requirement that the indices of an array in a computer programming language have to be integers, still conceptually this is what's going on. Now, remember our update equations. Any place where we can make a central difference in space and time, we can do an update. All right? So we get the spatial derivative here of HY, and we relate that to the temporal derivative of EZ, and then we can go, if we know these values of HY and this value of EZ, we can go to the next value of EZ. And likewise over here, let's say right here, we can make a central difference in space and time. And if we know these values of EZ and this value of HY, then we can leapfrog into the future here to get the next value of HY. Now, this breaks down over here. If we want to go from this value of HY to that future value of HY, we would need a central difference about this point, and we would have a central difference in time, but we have no point on the right, no electric field point on the right with which to make a central difference for the spatial derivative. So what do? Well, we have a similar situation over here. Suppose we want to go from this electric field point to that next one. We would need a central difference here. We have that in time, but we don't have it in space. Okay, so this is our problem. How do we do the update equations for HY at the right end of the grid? That's this problem over here. How are we going to update HY when we don't have a corresponding EZ to form the central difference for the space derivative? And likewise, for the EZ at the left end. over here. What do? We don't have an HY over here to the left. Now, what we did previously is we said, well, let's just then not update the HYs at the very right end. These values, just keep them 0. And don't update these EZ values at the very left end. Just keep them 0. But what is it when you have a medium in which the EZ is, no matter what the fields are, is always 0 at some point? Well, that's a PEC, perfect electric conductor. You always are shorting out the electric field. That's exactly what would happen if you put a perfect electric conductor at that point. Well, what's going to happen physically? You're going to get reflections. And likewise over here at the right, if the HY is always equal to 0, no matter what the fields are, well, that's like a perfect magnetic conductor. It shorts out the magnetic field. So we saw that in the reflections from the left and the right ends of the grid in our previous simulations. So what can we do? Well, in one dimension, there's a elegant solution to this, a simple, elegant solution. We're going to assume that mu relative is equal to epsilon relative is equal to 1, meaning at least near the edges of the grid, left and right ends, that we're in free space. Okay. And so let's say this is true at left and right ends. And another thing we're going to assume is that the Courant number, which remember the Courant number is the speed of light, that's in vacuum, times the time step over the space step. Okay, remember this is your space step, and this is your time step, that's equal to 1. We saw if we made it even a tiny bit bigger than 1, the simulation became unstable. But if we assume that that's equal to 1, what does that mean? That means then that for a wave that's propagating, c delta t, which is the distance it moves in one time step, is equal to delta x. Well, let's go over here to our grid and let's just plot that out. So consider this value of hy right there. In one time step, that would be going from here, which would be q1/2 to q1 plus 1/2, it travels one spatial step in one time step. Well, that would look like this. In other words, under this condition, this value would propagate and then end up as that value. In one time step, it would go one space step to the right. And over on the left, if we take this electric field value and we say that over here on the left, we have only fields that are propagating to the left because all the sources are somewhere in between the left and right edges, then this would propagate like that. Okay, so what does that mean mathematically? And we'll call this is a simple version of what we'll call an ABC, an absorbing boundary condition. And we'll go into absorbing boundary conditions later in more detail so that we are able to handle the situation where you don't have mu relative equals epsilon relative is equal to 1 at the left and right edges of the grid. But all we need to do then is, thinking back how we program these things. So for the hy, what we'll do is we'll say hy at the edge, which is hy element size, is going to just be hy of size minus 1. All right, so whatever this is, let's say it's 200. Well, hy at 200 is just going to be, at the next time step, going to be the previous hy 199. So we just simply make this assignment. And over at the left side, we're going to say then that ez of 1 at the next time step is the old ez at 2. So we'll say ez of 1 equals ez of 2. So we just propagate this value one space step over in one time step, and propagate this value one space step over in one time step. Here we go to the right, here we go to the left, because we assume all the fields are generated somewhere inside, and so if they're propagating, they're going to propagate to the right over on the right side and to the left over on the left side. Now again, keep in mind, and we'll look at this in the simulation, this fails if, say, epsilon relative is not equal to 1, or if mu relative is not equal to 1, and we'll look at this. Okay, so in general, we'll have to come up with something a little more sophisticated, but this should work if these conditions are true. So let's take a look at that. So here we are with our code corresponding to program 3.4 in the Schneider text. And this is where we left off last time. Let's go ahead and run that. So here we have a source in the middle. Okay, and we get, let's run this for a short period of time. Remember that if it's the field is propagating to the right, the algebraic sign of the EZ and the HY are opposite, like shown here. And if it's propagating to the left, they're the same. And we're multiplying, recall, when we do the plotting, we're plotting HY times the impedance of free space. So that makes the magnitudes of the E and the H the same on this plot. Okay, so let's go back to 200 time steps and watch what happens at the right and the left ends of the grid. Let's look at the right end first. Here we go. Notice the electric field gets very big and the magnetic field goes to 0. That's the PMC surface. So the magnetic field shorts out. Now let's look at the left side. Now watch, the electric field gets very small and the magnetic field gets big there. That's the PEC side. Okay, so this is the problem we want to overcome. Well, we've said that there's a simple solution. So let's go up here where we're updating the magnetic field. And before, and remember here, the way we dealt with this problem of updating the rightmost value is we just stopped this update loop before we got to m is equal to psi. So we don't update the rightmost element. Okay. So let's do that here. We'll say A, B, C at right side. And it was that we make HY size equal to HY size minus 1. Okay, and then we go through, and now that HY size minus 1 gets updated according to this. Now that should take care of the reflection at the right side. Let's run this again and see what it does. So over here. Ah, magic, yes. The field just went right through the boundary as if it was going off to infinity, as if it was being perfectly absorbed. So indeed, it acts as an absorbing boundary condition. Well, let's do this at the left side. So ABC at left side, and that was our idea there was to set EZ1 equals EZ2. All right, just propagate the second spatial sample over to the left. And now if that works, this should just propagate through, and there we go. So we generated these fields, and they just went off, and to the left and right, and as if they were going off to infinity, or being perfectly absorbed. So those are very simple absorbing boundary conditions. Now, we said it wouldn't work if the dielectric constant or the relative permeability were not equal to 1. Let's see. So over here, if we had, let's say, a dielectric constant of 2, this impedance, imp 0, which is eta 0, which is about 377 ohms, say would be divided by 2. So let's run that and see what happens. Okay, smaller electric field, bigger magnetic field, and there's a little bit of reflection at both sides. Okay, or if the mu relative was, say, 2, over here, divide that by 2, that also should not work. Or, yeah, it's not. There's a little bit of a reflection. Okay, so it only works if, at least at these left and right edges, you have free space. Now, likewise, it wouldn't work if the Karat number was anything other than 1. And remember, we looked at that. If we put a number here, like 0.9, and here, 0.9, okay, a little bit of reflection. Okay, so it only works in this very special case. Okay. Well, it's a very simple, elegant solution, but for more complicated cases, we're going to have to do something a little more sophisticated. But it's good enough for now for us. Now we can generate a field here at any space bin, and it'll just propagate off forever. At least it'll appear to propagate off forever. In fact, it just, the way this simple updating effectively tricks the algorithm into treating the grid as if it went off to infinity. Now, one of the things that we noticed was when we used this additive source, and we wrote something like, say, EZ at m equals 50 becomes EZ at m equals 50 plus some f of q. Q is the time index. Now, what we saw in the simulations is that produced two waves. So one that went to the right had an electric field and a magnetic field that were opposite in sign, something like this, and this was propagating to the right, where this is the x direction, and the other, oops, let's do that a little better, had electric and magnetic fields which had the same sign, but propagated off to the left. So why is that? Why do we get two fields, one propagating to the left and one to the right? Well, let's remember what these arrays, like EZ and HY, are representing. They're representing the magnitudes of vectors. So here's X, Y, and Z. And if we have a field propagating to the right along the z-axis, along the x-axis rather, remember that would have, say, a positive EZ component, and then, right, this is representing a plane wave. So in a plane wave, you've got the cross product of EZ, well, of E and H gives you the pointing vector, the direction of propagation. And so to propagate to the right, we'd have to have HY negative. And then that would give us a pointing vector, which would propagate us in the x direction. Now, to go the other way, for this other wave, here, go on to the left, if that had a positive EZ, then it would have to have a positive HY, so that EZ cross HY there would give you a propagation pointing vector going to the left. All right, so let's call this is the right wave, or let's just call it the R wave, and this is the L wave. Okay, so at the source, where, say, at m is equal to 50, where we're introducing a change only in the electric field, if you take these two plane waves, what you have is E right Z plus E left Z would be, say, equal to 1. In our simulations, if this had a magnitude of 1, we saw that these each had a magnitude of 1/2. So right when these are on top of each other, you get a half plus a half for the electric field would be 1. But the magnetic fields would be opposite, equal in magnitude, but opposite in direction. So H right y plus H y left would be equal to 0. So if you only add in a source term to the electric field, what that physically represents is the superposition of two plane waves, one going to the right and one going to the left, so that their magnetic fields cancel out and you're not adding anything into the magnetic field. But what if we wanted to create a field that only propagated to the right? This is our question. So say a rightward plane wave. Well, just from this illustration here, we're going to have to not only add something into the electric field, but also into the magnetic field. So we create the appropriate components for a plane wave propagating to the right. Now, notice that in general, function f of t minus 1 over cx propagates to the right at speed c. And since we call t q times delta t, right? Q doesn't have to be an integer here. And then we call x m times delta x. This is the form that this function would take. This is a solution of the wave equation that propagates to the right. And let's do this. Let's say that's f of, and let's factor out a delta t here. So we'd have q minus, to factor out a delta t, we got to put 1 in the denominator. So that'd be minus m delta x in the numerator and c delta t in the denominator. Okay, and then we factored out a delta t. Now, this is the inverse of the Courant number, and we're taking the Courant number to be 1, so that's 1. And so this has the form f of q minus m times delta t, and now let's call little f, where we just cancel out the delta t, and this little f q minus m. Okay, so this would represent a field that's propagating to the right at the speed of light. Okay. For a rightward propagating plane wave, we have this relationship between electric and magnetic fields. The hy would be minus 1 over eta 0 Ez, just going back up to this picture here. The ratio of electric and magnetic field in a plane wave is, in free space, is eta 0. Okay, and the magnetic field for rightward propagation has a negative algebraic sign relative to the Ez. So here's what we can do. Our Ez at time step q in spatial position s, this is going to be our source, but s equal to the m value at the source, where we're going to add the source in. So E sub z at time step q position s will be that value, plus we'll add in this rightward propagating wave f of q minus s, where f can be any function. So what about for the hy? Well, hy, and remember that the magnetic fields are offset by 1/2 time step and 1/2 step in space. Well, that's going to be, and the m is going to be the source point here. So that's going to be whatever value came out of the update equations, plus we add in this plane wave component, which is going to be minus 1 over a to 0 f of, well, let's see, for q, we've got q plus a half, and then minus, and for m, we've got s plus a half. And notice what happens here. 1/2 minus 1/2, that cancels out. We just get f of q minus s. So in our programming notation, we would just say Ez of s equals Ez of s plus f of q minus s. And let's just shift the time axis so that we just call this f of q. And then hy of s, we drop the plus 1/2 here for the magnetic field. And we just then now are subtracting minus 1 over a to 0, that same f of q. Okay, so if we take one of the spatial positions, one of the m values, to be the location of our source, and if we simply add some function of time into the Ez component there, and subtract 1 over a to 0 times that same value from the hy, we should get a plane wave that propagates to the right. Okay, so this is our claim. Let's see if that works. Okay, here's the code where we left off, where we had added in the absorbing boundary conditions at the left and right side. So let's just run that. Here we have a source here in the center, and it propagates off both directions. So let's do this. Let's call a constant src for source. Let's put it at bin 100. And this was the additive source, right, where we just add in something to the electric field. And again, that caused two plane waves, one to go to the right, one to go to the left. So we want now to change that. And we want to do add a rightward plane wave at the source. Okay. And so what I'm going to do up here is we're going to first do that for the magnetic field, because we're updating the magnetic field here. So let's do that here. Add rightward plane wave at source. And so we'll put that function here. Let's first call that function just f, so we don't have to calculate it a second time. And we'll say hy at source is equal to hy at source minus that f over the a to 0, which we call impedance 0, imp 0. Okay? And now down here, we just add f to Ez at source. Now, let's see what that does. Let's look over here. We generate a saw. Notice we just generate a field only that goes to the right. There was no component propagating to the left. Now, by the way, if we didn't make this a minus sign here for the hy, let's make that plus. What do we get? Oh, we get a field propagating to the left. Now, there was a little weird thing going off to the right there, and that has to do with the bookkeeping, that in that case, we really would want to take into account the offset between the hy and the Ez. Since we're propagating in the opposite direction, we wouldn't have f of q minus m, we'd have f of q plus m, and then the bookkeeping would be a little different. Okay, so the way we designed it was to go to the right, and there we go. So now we can make the source, we can put it at, say, at m is equal to 10. And here we go. Now we generate it over here, and there it goes off toward the right. And we've got the absorbing boundary condition. So everything seems to be working just fine. So now we can add in this field. Now, let's put it back to in the center. terminology is, see here, the incident field is only in this region in the right half of this domain. So any fields that would be in the left half would have to be scattered fields, fields that then interacted with this incident field and created a scattered field that then propagated toward the left. So we call this, to the right here, a total field region. It has both an incident and any scattered fields. We don't have scattered fields yet because we have just a homogeneous medium, just free space. But this would be the total field region, and then the left would be strictly a scattered field region. And so the boundary between them would be at this m is equal to 100, this source point, and that's where we're injecting this plane wave that propagates to the right. Let's now turn to the topic of inhomogeneous media. So this would be media in which the say the epsilon relative was a function of position and or the mu relative was a function of position. Now, one of the beautiful things about the finite difference time domain method is that it's so easy to deal with inhomogeneous media. We've played around a little bit with this as far as making the entire medium have a different dielectric constant or a relative permeability. So we would have something like this. Ez of m, our update equation would be, that would be equal to Ez of m. And then here would be the central difference for hy, for the spatial derivative, hym minus hym minus 1. Then that would then be times the eta 0, which we in the program called impedance 0, imp 0. And then if we had an epsilon relative of some value, we could just put that here, eps r. Okay? And we played around with that. And remember, in our notation for our programs, there is an implicit plus a half for the spatial index here. So this would be hym plus a half. That'd be to the right of the ezm. And this would be m plus a half minus 1, which would be m minus a half. So this would be your central difference there. And of course, also, we don't explicitly show the time index, but there's a offset of a half too for the magnetic field. Now, all we need to do to accommodate inhomogeneous media is just simply make this epsilon relative an array that has different values at different positions in space. And for the hy, here's our Ez, m plus a half minus m plus 1 minus ezm, and that would be over imp 0. And if we wanted to then have a mu relative, we could put that here. No Greek mu relative. And again, remember, so here would be, this would really be hym plus a half, and this would be m plus 1 and m, so this would be a central difference there. And again, if we wanted that to be inhomogeneous, we just make that an array. So that's all we have to do to handle inhomogeneous media. So we're going to look at that in a minute on the computer. Before we do that, though, let's just make one little other additional change. Here is in space, and here we've got our electric field values. And remember that our magnetic field, well, let me draw another time step here. And our magnetic field values are offset by one half of a step size in both space and time. And what that meant was our absorbing boundary conditions over on the left had to do with doing this operation here, where the electric field at m equals 2 was then assigned in the next time step to the m equals 1 value. And on the right, we did that with the magnetic field. Now, let's do this. Let's just get rid of the rightmost magnetic field sample. In other words, we're going to have one fewer elements in the array of HY values than in the EZ. So that now the grid terminates on both the left and the right with an EZ. Now, this really isn't a big deal for the problem we're doing right now. But later, when we look at more sophisticated absorbing boundary conditions, it's very convenient to have those apply to the same field components, both an either electric field in both cases, or it could be a magnetic field in both cases. So we're going to do the electric field. And now, in this case, we would be, I haven't drawn many samples here, but we would be doing the propagation now on the electric field component. So a small change, but it's going to be very useful for us later. So now we're going to have, for the left, we're going to say EZ1 is equal to EZ2. And remember, this we don't show explicitly the time index. So this means that the current value of EZ2 is going to be in the future, be the next value of EZ1, because this represents a field propagating to the left. And now we're also going to say EZ size, the rightmost E sample, is going to be EZ size minus 1. And this is going to do the propagation to the right for the electric field. Okay, so let's make these changes. So here's where we left off with our program. We were able to inject a plane wave moving only in one direction. And we have absorbing boundary conditions at the left and the right. Now we did the ones on the right in terms of the magnetic field. So let's come up here and let's have one fewer magnetic field sample. So that means here now, we're not going to have this absorbing boundary condition. Now when we come down here and we say, we do this update in EZ. Now notice HYM, when M is equal to size, there's no longer an HYM size. So we're going to have to do one fewer of these. So we do one fewer step on the left and on the right now. And now we add in here, EZ size is EZ size minus 1. This becomes our absorbing boundary condition at left and right sides. So let's see if that works. Yeah, so it worked. That worked fine. Now we are just using the electric field for the absorbing boundary conditions at both the left and the right side. So now we want to make our medium inhomogeneous. So let's come up here and let's just do an epsilon relative, the same size as EZ, but we'll make it 1s by default. And we could also do a mu relative, but we won't do that here. And then we just need to, let's do more time steps here. And now we're just going to find the eps relative value. So we'll do 4. M equals 1 to size. This will be we'll go through and let's see. They're already defined to be 1 by default, so we just have to define the regions where we want it to be different than 1. Let's do this. Let's move our source over to, say, 20 here in the grid. And let's put, starting at 80, so we'll say if M is greater than or equal to 80, and M less than or equal to, let's go from 80 to 140. If that's true, let's make eps relative M equal to 4. Okay? All right. Now, we have to update our easy update equation. It's got to be, we've got to divide by F's relative of M. So let's see what this does. So we generate a plane wave. Okay, let's change the scaling on this so we can see better what's going on. So the vertical scaling, we'll change that. Delete that guy and start over. Here we go. It should hit, yeah, it hits a surface right there. There's a reflection. Now notice when it's in the medium, then it hits the back wall, and then there's another reflection. So let's actually just look at this here. So notice when it's in the medium, the impedance is different. Not only that, the speed is different. Right? So the square root of epsilon relative is 1/2. This thing is moving at half the speed of light in free space. So let's look at that again. Watch the reflected field and the transmitted field, the relative speeds. This is half the speed of that. And also the impedance, right, is the square root of mu over epsilon relative. That's also 1/2. So in this case, the electric field is 1/2 the amplitude of the magnetic field. Okay, now let's go for the longer duration. Here's a reflection and transmission. And there's going to be another reflection at the back wall and transmission out there. Notice that goes faster than this one comes back. Now there's a reflection and a transmission. And then it hits the back wall and there's another reflection and transmission. Of course, it gets weaker every time that happens because you divide up the energy. Some of it gets transmitted, some of it reflects. Okay, so now we're solving a fairly non-trivial problem. Now this is one you can solve. It's a little bit, takes some not non-trivial analysis to do that for plane waves on a dielectric window. But now we can do something like this. Let's come in here and make this something like 4 times the sine of m minus 80, then times pi. So when m is equal to 80, this will be sine of 0 will be 0. So we're going to have it be 1 plus this. So let's make that 1 plus 3. So it'll be 4 when this sine gets to its maximum value. So m equals 80, we'll get this term will be 0. And then we want it also when m is 140. So we'll do m minus 80 over 140 minus 80. Okay, so when m is equal to 80, this will be 0. When m is equal to 140, this will be 1 times pi will also be 0. So let's take a look at that. So there should be, it comes in here. You notice the change, a much smaller reflection, and there's a gradual transition. Right? So this is a much more complicated problem. You'd have to use like a power series method to solve this analytically. Let's look at that again. Okay, so it kind of slowly eases into this medium. There's a smooth transition and reflections and transmissions, etc. Okay, we're now solving very non-trivial problems that you really can't very effectively solve analytically in one dimension and without a lot of code, right? The basic ideas are very simple. So this is one of the big attractions of the finite difference time domain method. The coding, right, is very simply, conceptually very simple. Is very simply implemented. And now when we extend this to 2 and 3 dimensions, well, now we're going to have more loops and more variables and things, but it still has this same relatively simple character. We're just applying central differences to represent spatial derivatives and temporal derivatives, and we can implement and integrate inhomogeneous materials very simply, very elegant in that sense. Now let's turn our attention to the subject of lossy media. Right, and this is going to be, we're going to limit our consideration here to a medium that has a conductivity, sigma. And what is the significance of that? Well, if we have an electric field, then we will get a current density, J sub C, we call the conduction current, which is sigma times the electric field. This is Ohm's law for the electric field. And in general, we can break up the total current density as an impressed current density plus this conduction current density. So an impressed current would be one that somehow we force into our system. And this is actually the term that we use to introduce sources into the Yee grid. So we're going to add this idea right here. Okay, so what happens? Well, let's see. So then we have Ampere's law now looks like curl of H is equal to, and let's neglect impressed current. We've already dealt with it in introducing our sources. So let's just add in this conduction current. So sigma E plus epsilon time derivative of the electric field. In one dimension, then this gives us the equations sigma Ez plus epsilon dEz dt is equal to the x derivative of Hy. Okay, so this is the new term here. Now there is a subtle issue that goes on in this case. So here is an electric field point. Another one. And there's a magnetic field point here and there. And so this is Ez at time step q plus 1 at spatial position m. This is Ez at time step q, spatial position m. This is Hy at time q plus a half, spatial position m plus a half. And this is Hy at time q plus a half, spatial position m minus a half. And with these 4 points, we have the two central differences, our space derivative and a time derivative, right? And so this is what we base our update equations on, making a central difference at this position and time. So then that allows us to solve for Ez at the next time step in terms of the known Hy and previous Ez value. How do we fold this term in here? Well, notice in this case, there's no derivative in that term. So we're trying to write this equation at this point here, right? And we do it with a spatial central difference and a temporal central difference, but this term is not a difference. It's not a derivative. So we need, well, let's do it in red here. We need, Ez at spatial position m, but at time q plus a half. Now, how are we going to get that? We know Ez at m at time q, and we're trying to figure out at time q plus 1, but to do that, it appears we need to know it at time q plus a half. Well, what we could do is to say Ez at time q plus a half. Well, a reasonable approximation is if we knew it Ez at time q and at q plus 1, then the average of those might be a reasonable approximation to EZ at time Q plus a half. So let's write that average here. EZ at time Q plus 1 plus EZ at time Q divided by 2. That would be the average. Okay, so let's use that for our value of EZ right there at the center of those central differences. So we're going to use that for that term right there. Okay, here's what we get then. We'll have sigma times EZ, which we're going to write as this average, EZ Q plus 1M plus EZ QM over 2, plus, now got the derivative with respect to time of EZ, so that becomes, we got epsilon times, and then we'll do a central difference there. This is EZ at Q plus 1M minus EZ at QM over the time step delta t. And that's going to be equal to this spatial derivative, which is going to be a central difference. So we'll have HY, and that's at time step Q plus a half here. M plus a half minus HY. Oops. Q plus a half, M minus a half over the spatial step size, delta x. Okay, so this is the new term here. We already solved this for these two terms. So let's do the following. Let's multiply through by delta t, gets rid of that. We'll have a delta t there. And let's divide through by epsilon. So we get here over an epsilon. And if we do that, then we can isolate the EZ at time Q plus 1 from these two terms, and we'll write it this way. EZ at time Q plus 1, position M, times, here we've got 1, plus, and here we've got a delta T sigma over 2 epsilon, which we'll write as sigma delta T over 2 epsilon. Okay, that's going to be equal to, now we're going to take the EZ at time Q and move it to the other side, so this guy will become a 1 times that. So here we'll have EZ at Q, terrible, at Q, position M, 1, and then here this plus becomes a minus, so it'd be minus this same term, sigma delta T or 2 epsilon. And then over here, we're going to have delta T over epsilon delta X. Times HY at time Q plus a half, position M plus a half, minus HY at time Q minus a half, position M minus a half. Okay. And of course, now what we can do is just divide by this factor right here. But first, let's note that this term right here, at least when we take the Courant number to be 1, we already said that this is eta 0 over epsilon relative. And let's define this term right here. So if we actually know what the sigma value is here and the epsilon, we would actually have to figure out what the delta t would be. But let's just call that whole term L for the loss constant. Then we can solve these update equations as EZ at Q plus 1 at M is equal to, well, we're going to have the EZ at Q 1 minus L over 1 plus L. We're going to divide by this factor here. So we're going to have 1 minus L over 1 plus L EZ at QM. Oops, and this shouldn't have been equal. This should have been plus there. Sorry about that. Plus, here's eta 0 over epsilon relative over 1 plus L. And then times this difference of these HY terms. So there is our update equations. Now Schneider calls this term right here an element in an array CEZE at location M, and this term is an element in an array CEZH location M. And so in our programming terminology, this would be EZ at M equals this CEZE of M times EZ of M plus CEZH of M times HY of M. Remember, we dropped the plus 1/2 minus HY. Then this would become, subtract a half, so M minus a half minus a half, M minus 1. Okay, so that would be our new update equations if we had loss. Now, of course, if the sigma, the conductivity, is 0, the L factor is 0, so then this CEZE is just 1, and then this just becomes, and this is 1 plus 1, I'm sorry, 1 plus 0 here, sorry. And so this just becomes eta 0 over epsilon relative, which is what we had before. So we just recover the original inhomogeneous dielectric if we allow epsilon relative to be a function of position. But now we can introduce conductivity. And the Schneider text also talks about introducing a fictitious magnetic conductivity, which would have no meaning at DC for non-oscillating fields, but at high frequencies can represent the loss mechanisms in magnetic materials. We won't go into that, though. We'll just stick with normal electrical conductivity. So let's modify our code as shown here. So here we are where we left off with our code, and this allows us to do the inhomogeneous dielectric constant. Here we go. We've got a medium right here. We got a reflection, transmission into the medium, a reflection at the back wall, absorbing boundary conditions, another reflection from the front wall, and etc. Okay. So here's what we're going to do. We're going to change, instead of this eps relative, we're going to make this is that CEZE array. It'll all be ones, and then there's the CEZH array. And that's going to be the one that multiplies this term right here. That's got an eta 0, imp 0. Let's put that up here so we don't have to keep doing that multiplication. Okay, and then this will become the CEZH term. And over here we'll have CEZE. M times EZ, and that's the only changes we need to make. So over here, we'll say in this region, eps relative will be 4, and the loss term will start off with 0. So it should just recreate the scenario we just looked at. And the CEZEM, that's equal to 1 minus the loss over 1 plus loss, and CECH is equal to the eta 0 or imp 0 over the EPS relative over 1 plus loss. All right, if we did that correctly, we should see exactly the same result we just had. And there we go. But now we can put in some conductivity effects. Let's make this loss term 0.01. Let's see what that does. Here comes our field, goes into the medium. Now notice that amplitude starts to drop off. That's lossiness. Now the reflected one, so everything is decaying exponentially inside that medium. If we make this loss term 10 times as big, here we go into that medium, and wow, that just really decays extremely rapidly. Okay, so now we've implemented lossy material in terms of a conductivity, which is hidden in this loss factor L here. And of course, this could be also a function of position. We just did it here, just a uniform medium, but piecewise constant properties. But this could be something that varied with position. So if we also included the magnetic conductivity, now we could vary electric conductivity, magnetic conductivity, dielectric constant, and relative permeability arbitrarily with position. And now we can solve quite complicated one-dimensional problems. In fact, we can solve the most general one-dimensional problem with this code, right? And we didn't have to change very much, right? So there's just about one page of code here. We made small incremental changes as we added these different features into our code.